I'm Issy Rafferty, and this is me and Emmanuelle Hagopian's video on UV vis spectroscopy.
In ultraviolet visible spectroscopy, we can either be dealing with single beam or double beam instruments. Here we're dealing with a double beam instrument. In ultraviolet visible spectroscopy, a beam of light from visible and or ultraviolet light is separated into its component wavelengths through diffraction grating or through a prism. Each monochromatic wavelength is then split into two identical beams, which is sent simultaneously through the sample and reference cuvettes. However, another alternative is that the light passes through the sample and reference several times per second as directed by a rotating mirror or a chopper, otherwise known as a chopper. So, using a double beam instrument, we have
This allows us to measure how light is transmitted through both, and therefore the difference between them. The reference corresponds to the baseline, allowing us to just measure the absorbance of the sample. It's important to auto-zero the machine before starting, as this decides the point which is absolute zero, so no shifting will occur during the experiment. First, we set the baseline, which involves putting 2 cuvettes of solvent in the machine. This cancels out any background noise or any peaks that are due to solvent and not the sample.
So originally we're measuring the two reference points, which are the solvent. So we put the solvent in here and the solvent in here. Here we're filling up the reference solution, and you can see that we are only handling the sides of the solution and not the faces, because this will mean that grease is on the sides, which will interfere with the spectra. In UV vis experiments, 1 centimeter path cuvettes are used, and we can choose between quartz glass, or plastic cuvettes. The difference between quartz and glass cuvettes is that the former makes a much larger window available and thus is useful for analysing species, which absorbs at wavelengths lower than 350 nanometers. Cuvettes are examples of sample holders, and there are several ones that depend on the sample type, the amount, and the stability of the sample. For example, cylindrical cuvettes are used for gas phase samples, and a longer path length one is suitable for weakly absorbing gases or low concentrations. Micro cuvettes here are useful when the sample is in small amounts or it's expensive, so you want to use the smallest amount of the sample. They do this because they maintain the 1 centimeter path length. However, the thicker side of the walls reduces the volume. The 1 millimeter cells serve the same purpose, but where the signal is not concerned, that is, the sample has a sufficiently high extinction coefficient to generate absorbance. Flow cells here supply a continuous flow from a reservoir. They're used where sample degradation is a concern, or where the external influence to the sample is to be monitored. Other cuvette examples include thermal cells and electrochemical cells.
It's important to use identical cuvettes so you do not introduce a systematic error in your experiment. The cuvettes must be filled 3/4 full and pushed down fully into the machine, as well as being capped and having no bubbles or sample on the sides. Inserting the sample.
Having set the baseline, we are now inserting the sample, which is the sodium chromate, into the cuvette, which will then put it into the detector to measure it through ultraviolet visible spectroscopy. So the detector measures I and I naught, which thus allows us to determine transmission and absorbance. The absorbance at any wavelength is related to the intensity of light passing through the sample. The wavelength is related to the energy of the light.
Yeah. We've run the UV vis from 800 to 350 newton meters wavelength range and seen a large peak here of absorbance. The colour of the sample is yellow, so we would expect that it would absorb violet light in the range 380 to 420. From our results, we can see the absorbance peak between this range.